Hello, I am Giovanni Reina and today I present you a study on collective foraging I have conducted at the University of Sheffield with James Marshall. Collective foraging is regulated by social insects through a combination of positive and negative feedback signals. Positive feedback is a mechanism to recruit other insects and reduce the efforts of individual exploration. Negative feedback, instead, is a mechanism observed in some species to indicate that the food source is not ideal. Why not ideal? Because either the environment has changed and food disappeared, the food source is overcrowded, or a predator has been located at the food source. We propose an alternative function that could motivate the use of negative feedback also in static environments. Negative feedback gives variance reduction on the group distribution. This work is a theoretical study based on collective foraging model of honeybees. However, given the model's simplicity, it matches the foraging behavior of some ant species. The model is simple and includes 4 transitions that an insect could do to change its foraging behavior. 2 individual transitions that are discovery and abandonment, and 2 social transitions in response to signals received from other insects of the colony. The insect can get recruited as a form of positive feedback, and it can get inhibited as a form of negative feedback. We can represent the model as a set of chemical reactions in which we represent the foraging state with a color. Blue for insect foraging at the blue source, and green for insect not knowing where to forage from. We can then represent the fourth transition as a change from an initial state to a final state with a certain transition rate indicated on the arrow. We have the 2 individual transitions and the 2 transition conditional to interaction. And for more food source, the reactions are simply replicated and the model scales to any number of food sources. The insects modulate the frequency of their action as a function of the estimated of the quality of the food source. They do so in order to reach the desired group distribution that here is represented as linearly proportional to the quality. In this study, we focus on the role of negative feedback on group dynamics and the resulting group distribution. Therefore, we compare the model without negative feedback, where we set the transition rate to approximate the desired distribution, against a system with the negative feedback, which has the additional transition of inhibition, and it also has a change in the transition rates. As the 2 models are different, to approximate the same distribution, the rates must be different. So we perform our theoretical analysis comparing the 2 models. First, we show that using ordinary differential equation, assuming an infinite swarm size, we have that both models converge to the desired distribution. Then, when we complement the analysis approximating the solution of the master equation via the Gillespie algorithm, we see that the dynamics are very different. The bottom plots show 30 representative trajectories. The system without negative feedback often converge to value very far from the target distribution. The box plot on the right of each plot is the aggregate of 1000 simulations. You can see that the mean is indeed centered around the predicted value, but the spread on the left plot is very large. On the right, instead, the system with negative feedback has a relatively small deviation with values centered around the target distribution. We further analyze and compare the 2 models by varying their parameters. We vary the swarm size, the recruitment strength, the quality of the food source, or the numbers. We always find that the system without negative feedback has a variance much larger than the system with negative feedback. By varying the negative feedback strength on the horizontal axis here, we find that it can regulate the speed robustness trade-off. Increasing the negative feedback, we have a reduction of the convergence time and an increase of the error, that is the deviation from the target distribution. Therefore, the colony can manage this speed robustness trade-off to react to situations that could benefit more from speed or precise distribution. So, to wrap up, we know some of the reasons why negative feedback is used in social insects. They use it in collective decision making, to break symmetry, and in collective foraging to quickly react to time-varying environment. I have shown you today an additional important role of negative feedback, that is variance reduction. We don't know if this function is the reason why negative feedback evolved in some species. Our analysis show it reduced the deviation from the target distribution and can, in this way, be evolutionarily advantageous. This concludes our analysis. I hope you liked our work and you find it interesting. Please post any comment or question in the comments section. Thank you for watching.